So hello to all my young friends who are studying in intermediate and they are watching this video. Welcome to the lectures of GTK Academy. In our previous video, we had covered uniform circular motion, which was a very important topic. Today, again, we are going to discuss an extremely important topic of mechanics, which is work power and energy. Needless to mention that not only from intermediate point of view, even from competitive exams point of view, these all chapters are extremely important. And of course, work power and energy is very important. I have tried my level best to present you in a very simple manner so that all your concepts are clear, along with some good examples which I'll be solving. And I have always advised you to pause the video and try to solve them yourself. In this way, you will be practicing along with me. After that, you can practice more problems from your textbook or whatever the sources that are available with you. So I expect that you will derive the maximum benefit out of this video. And also, I request you that you watch this video fully. Now, without wasting much time, let us start our topic, which is work power and energy. Let's start with the basic definition. Now, basic definition, which is in front of you, that says whenever a force acting on a body produces a change in the position of body, work is said to be done. So, work is said to be done only when a body acted by a force moves through some distance in the direction of force. This is very important. In your junior classes, you must have read that work is equal to force into displacement in the direction of force. So this definition you all must have studied in your junior classes. So work is said to be done only when the body acted upon by the force moves through some distance in the direction of force. You can see a pictorial example where a force is applied on this body and this is being pushed along this inclined plane. So work is done because force is in this direction and displacement is also in this direction. Now force can be constant and force also can be variable. You can have the cases where you have a constant force, and also you can have some cases where the force varies with time. So let's discuss work done by a constant force. Then we will discuss work done by a variable force. Now work is measured by the product of the applied force and the displacement of the body in the direction of force. This is what we had discussed just now, and this is what in fact you must have studied in your junior classes. So how do we measure the work? We measure the work by the product of the applied force and the displacement. This is very important, in the direction of force. I am again reiterating, please clear all your basic concepts here. So, if you have a body here and you apply a force F here, and this body moves by a distance S, now what will be the work? Work done by this force. That will be force into displacement of the body in the direction of force, which is S. So in this case, work is equal to F into S. Work done by the constant force. Please note this. Work done by the constant force. Now, if the force is making an angle theta with the direction of displacement, say in the previous example, this is the body, and instead of force in this direction, which we discussed just now, we have the direction of force like this, which is making an angle theta with horizontal, and the displacement happens in this direction only. So the body moves now by a distance of s. So the displacement is s, but direction of force is a bit different from the direction of displacement. Now, how are we going to calculate the work in this case? Any guess? Just pause the video and think for some time. Probably some of you may be able to guess it, and I hope that many of you must have guessed it correctly. Anyway, we'll just rewind it. Now, what we'll do, we'll resolve this force into two components, F cos theta and F sin theta. And now we'll again replay it. Now you can see that this is the direction of displacement. The component of force which is in the direction of displacement is F cos theta, and the component of force which is perpendicular to the direction of displacement is F sin theta. Now, the whole displacement happens in the direction of F cos theta, and in the direction of F sin theta there is no displacement. So work should be, in this case, should be F cos theta into S. That means work is equal to F into S into cos theta. Now you know that force is a vector quantity and displacement is also a vector quantity. So we are multiplying two vectors and we are getting a work which is a scalar. Now when we multiply two vectors and we get a scalar, then it is called scalar product or dot product. So it is written as F dot S, which is mod of S into mod of F into mod of S into cos theta. That is what we are getting it here. Hence, work is a scalar product of force and displacement. I think it is clear to you. If you write in vector form, work is equal to F vector dot S vector. Now, units and dimensions of work. Let's first talk about dimensions of work. What will be the dimension of work? See, work is equal to force into displacement. Now force is equal to mass into acceleration into displacement. The unit of mass is m, acceleration is L t minus 2, and s, unit of s is again L, length. So dimensions of work will be m L2 t minus 2. That's what we have written. Or you can also write Newton per meter, because force is written in Newton and displacement is in meter. Or you can write kg. Newton can be written kg into meter per second square into meter. So kg into meter square to second minus 1. You can write either way. So these are the dimensions of work. Now let's talk about unit of work. Work is equal to force into displacement, which is Newton into meter, because the unit of force is Newton. So this is called joule. In SI system, which we generally use, 1 joule is equal to 1 Newton into 1 meter. If a force of 1 Newton moves a body by 1 meter, then the work done is 1 joule. However, you have other systems also, like CGS system. CGS is centimeter gram second system. What is the unit of work there? Their work will be equal to force into displacement. Now, what is the unit of force in CGS system? That is dyne, into what is the unit of displacement? Centimeter. Now, this dyne into centimeter is called erg. So, 1 erg is equal to 1 dyne into 1 centimeter. Now we again know that 1 dyne is equal to 10 raised to the power minus 5 Newton, and 1 centimeter is equal to 10 raised to the power minus 2 meter. So 1 erg is equal to 10 raised to the power minus 7 Newton meter, which is joule. So 1 erg, so that means 1 joule is equal to 10 raised to the power 7 ergs. That's what we have written here. Hope you are clear. Normally, SI system is used, and you get most of the questions where the units are in SI system only. But if somebody to test your knowledge on this part mentions the unit of work in erg, you should not get confused. That is the reason why I have discussed CJ system also. Now, the nature of the work done. Work done can be 0, it can be positive, it can be negative also. Depending upon the angle theta which the force makes with the direction of displacement, work done is classified as. Now, let us first write here work is equal to F dot S. Now, that is mod S mod s into cos theta. Now we have three cases here. Theta is equal to 90 degree. Then cos 90 is 0. Work is equal to 0. Theta is acute. So cos of acute angle is positive. Then work will be positive. Theta is obtuse. Cos of obtuse angle is negative. So work will be negative. So we have these three cases. Work done by the force is 0 if theta is 90 degree. That means if your force is acting in this direction and the displacement is taking place in this direction where the angle between force and the direction of displacement is 90 degree, the body is moving like this. So there is no displacement in the direction of force. So that means the work done is 0, and you cannot have any component of this F in this direction because component of cos 90 will be 0. Work done is positive when if theta is acute, less than 90 degree. Like this. Here you will have two components, F cos theta and F sin theta, which we discussed just now. Now displacement is happening in this direction, that is direction of F cos theta, and there is no displacement in the direction of F sin theta, just leave it. But we are having some positive quantity. If theta is 0, so there is no component as in this direction. So now if you have a displacement in this direction, work done is positive. Work done by the force. Please note this. Work done by the force. Negative when theta is obtuse. That means work is acting, the force is acting in this direction and displacement happens in this direction. So work done is negative. Now again you can resolve this force into two components. One is this in this direction, one is in this direction. Now in this direction there is no displacement, but in this direction displacement is happening but in opposite direction. So work done by the force is negative, right? Now here important thing is we are discussing work done by the force. Now work done against the force is negative of that quantity. Now in first case, work done by force is 0, work against force, that is also 0. Here work done by force is positive, so work against force is negative. Here in third case, work done by force is negative, so work done against force is positive. I hope you are clear. This is a very basic uh, thing which I thought it is appropriate for me to discuss here, because at times people get confused in these small things also. So let's move. Now the nature of work done. Let's take some interesting examples. When is the work done? 0. When theta is 90 degree, which we have already discussed. A coolie, you must have seen a porter is called coolie in Hindi. He is carrying a load on his head, moving on a horizontal platform. And here theta is 90 degree. because the force acting is the force of gravity, and his movement is in this direction, and force of gravity is in a perpendicular direction. So the displacement is happening in this direction and force is in direction perpendicular to displacement, where theta is in 90 degree, and there is no work done by the force or against the force. I think now it will be more clear. This pulley or portal is moving on a horizontal platform. Force is acting in downward direction. So the angle between the force and displacement is 90 degree. However, if you tell a porter that you have not done any work and I am not going to pay you, there will be a big fight, because he is not doing the work against gravity, but definitely there is a work against friction, which we'll discuss later. Now, a satellite revolves in a circular orbit around the Earth. Here also theta is 90 degree. Hence, the work done by gravitational, which is centripetal force on the satellite, again it is zero. This is a satellite which is moving in a circular orbit around the Earth. So, the gravitational force at any point acts in this direction, which is a centripetal force, which keeps it moving in circular orbit. So, you can see that at any point, the direction of force, let me highlight in yellow, because direction of force is perpendicular to direction of displacement, and direction of force changes, uh, it's continuously changing, and the direction of displacement also, because the body is not moving in a straight line, it is moving in a circle, and every point the direction of force is perpendicular to the direction of displacement. So here also the work done by the force or against the force is zero. I hope you are clear with this. Now let's take the cases where work done is positive. If theta is acute, it may be any angle between 0 and less than 90 degree. Now, if a body falls freely under gravity, where theta is 0 degree, the work done by the gravity, that is the force, is positive. This is, two bodies which are falling, and force of gravity is acting in this direction. So the displacement is also taking place in the direction of force. So work done by the force is positive, by the force, or we say the force is gravity here. So work done against gravity will be negative, against the force. A roller is being pulled by applying a force along the handle, because if theta is acute, it may be that theta may be any angle between 0 and 90. It's not that theta is going to be 0 only. Now, here, this roller is being pulled by applying a force F in this direction, but the direction of displacement is this. So, the direction of force makes an acute angle, you can see, with the direction of displacement. Again, work done by the force is positive. When is the work done negative? When theta is obtuse. It may be any thing between greater than 90 till 180. Now, for example, a body is sliding on a rough horizontal surface. Here, theta is obtuse, 180 degree. Hence, the work done by frictional force is negative. You just see here. This is a rough surface, and these are two bodies, and this body is under motion going in this direction. Now force of friction will be opposing it. So the displacement is happening in the opposite direction to force, which is friction here. So the angle between the friction and the displacement is obtuse, which is 180-degree in this case. So work done by the frictional force is negative, but work done against the frictional force will be positive. A body is thrown vertically upwards. Here also theta is obtuse. We are throwing this body vertically upwards. And what is the force here? Gravity here acting in this direction. Displacement is happening in this direction. Now, the displacement makes an angle 180-degree with the direction of force. So again, the work done by the force, which is gravity here, is negative. However, if we say the work done against the gravity, that will be positive. Now, work done by a variable force. This is what we had discussed till now, was the work done by a constant force. But if the force is also varying, if the force is variable, like force on a rocket which is fired upwards, what happens once it starts going up? The gravity also starts decreasing. So the force on the rocket is varying. Or force on a stretch spring. If you have a spring and you start stretching it, the more you stretch, the more will be the force. So as you stretch the spring, if you are going to stretch, the force will be in this direction. If you are going to compress, the force will be in this direction. So the more you compress or the more you stretch, the more will be the force. The force increases with stretching or compressing the string. So again, the force is variable. Now, how do we calculate the work done when the force is variable? Here we are going to use calculus. Now, for example, if we draw the graph between displacement and the force, and it comes like this. Suppose if the force is constant, then it will be a straight line parallel to x-axis like this. But here you can see the force is varying, you know. Then how do we calculate the work done? Suppose we have to calculate the work done from displacement x1 to displacement x2. Now what we do, we divide this into very small strips. Take one strip at a distance x and say the thickness of this strip is dx. Now, since this strip is extremely small, this strip is very small. We can't, in fact, we can't show it here, but it is very small. We have to draw some, otherwise, if I make it very, very small, probably you may not be able to see it properly. So just in order to, make you see that, I have drawn it big. Now here, although the force here is also varying very slightly, but if it is very small, force can be considered constant in this small strip. So the small work done dW in this strip will be equal to force in this strip, which is we are taking constant, into small displacement, which is dx. So the work done total from x1 to x2 will be equal to integral f dx, and we integrated between the limits x1 to x2. So this will be nothing but this whole area A. So this is the area under the curve. So if you draw a graph between force and displacement, then the area under the curve represents the work done. I hope this is clear. Now, let's talk about one very important thing, which is conservative and non-conservative forces. Now, what is a conservative force? A force is said to be conservative if the work done by the force or against the force in moving a body does not does not depend upon the path, but it depends upon initial and final position. So what is conservative force? Conservative force is where the work done by force, by this conservative force in moving a body does not depend upon the path, but it depends upon the initial and final position. What do we mean by that? Suppose the body is at A and we take it to B. We can take it to through any route, like this, like this, like this, or like this. Now, if work done in this path is W, then in this path also it will be W. In this path also it will be W. And here also it's going to be W. Same amount. Whether W is positive, negative, that's a different thing. But if you are taking body from A to B, work done will be same irrespective of the path you adopt in taking the body from A to B. So one thing about conservative force is that the work done by the force or against the force in moving a body does not depend upon its path, but it depends upon initial and final position. Again, one more important thing is work done in a round trip is zero. That means if you take it from A to B and then you bring it from B to A, suppose you have done W amount of work from A to B, then from B to A, the amount of work will be minus W. That means the total work done will be W minus W, which is 0. Now, what are the examples of conservative force? Some examples are gravitational force, electrostatic force, spring force. These are all the examples of conservative force. A central force is a conservative force. Now, what is a central force? We are using a terminology central force. Central force is always directed towards or away from a fixed point. Suppose we have a fixed point O here. So at any point P, see we have P, just join it. The central force either it will be away from O or it will be towards O. You take any other point P dash here. Here also if you just join. So either the force will be away from this central point or it will be towards. So that is what is called a central force. And the magnitude depends upon the distance of the particle from that point. Suppose this is the central point O and we have a point P here. So which we already discussed that force will be away or towards O. Suppose this is in this direction force. Now and the distance is say x from O. So this force depends upon x. Now how is the relation? That is different thing. But this force depends upon x. Now let me again make it more clear to you. We have said what are the central forces? Gravitational, electrostatic, or spring force? Let me just give you some examples of that. Let's talk about gravitational force. You all know that this is our earth, and every body around the earth is attracted towards its center. Now let's uh, draw the lines like this. It's different dias. At any point, say a body is at this point P, the force will be towards center. If it is at this point, again the force will be towards center. If it is at this point, again the force will be towards center. So this is a central force. Now if we have a body at A and we move it in circular path, say like this, what is going to be the work done? Can you just guess? I think we just now discussed the work done will be zero in that case because there is no displacement in the direction of force. At every point, you have the force in this direction, and the direction of displacement is this, which is perpendicular. This angle is 90 degree. So there is no work done if you take it in a full circle, but if you take it from A to B, what will be the work done? Suppose the distance between A and B is x, and A and B are very close such that the value of G doesn't vary between A and B. So the force acting here will be m into G, where m is the mass of the body. So work done from A to B by gravity will be minus mg into x, because the direction of force is opposite to the direction of displacement. Now you take the body through whichever route, like this or like this, whatever route you take, the work done will be minus mg into if x is the distance between A and B. And if you bring it from B to A, so this is work from A to B, work done by force, by gravity. Work done from B to A will be mgx. So in a round trip, it is going to be 0. Similarly, if you have another point C, if you take the body from B to C, there will be no work because you have not moved in the direction of force. But if you take the body from A to C, you have moved this much x, which is the difference in radius of these two circles. So you can take from A to C through any route. Work done by gravity will be minus mg into x. I hope this is clear to you. This is the case of gravitational force. If we have electrostatic force, similar case, you have a place where there is a positive charge, central place, and then you have a test charge, minus charge here. You can again draw the same circles and line. Here we have spherical symmetry. Now, if you move this negative charge, because this negative charge is going to be pulled in this direction, wherever it is. If it is here, then the force will be like this. You can see here you will find spherical symmetry here, not only circle, because this is a three dimension. In space also you can take it. So if you take in a circle shown by red color and complete a whole circle, there will be no work. But if you take from A to B, again the same case what we discuss in the case of gravitational force, and whatever route you take, this one this one or any other route, there will be work done will be same. But from B to C, again there will be no work. But from A to C, there will be work done irrespective of the path you adopt. Now, in case instead of negative charge, you have a positive charge. Here, the force is directed in this direction. That's it. That is the only difference here. I hope this is clear to you. Now, what we will do, let's calculate the work done between 2 points A and B for different routes for a body under conservative force, which is gravity here. We are taking gravity, and then we will now show you how the work done is same irrespective of the routes you adopt. But here there is one small thing, small clarification, because some people get doubt. I'll clarify you on this account, especially when we are discussing this gravity. Now you all know that this is our earth and everything here is attracted towards center. Like G acts in this direction. Say in this place, G will be acting towards center. But as you go around the earth, the direction of G is going to change like that. See here the direction is different. Here it is changed. Here again there is a 90-degree between the direction at this place and this place. And here there is a 180-degree change. And as you go around, the direction of G changes. So some people at time get confused that if on the ground, if they are taking G like this, then after some distance, say a few meters, probably they may take it like this. No, this is not correct, because for 1 degree change happens in nearly 120 kilometers. That means 1 degree change, and a zero point 0.5 degree in nearly 60 kilometers. So if the distance is very small, we normally take it, parallel, we like this. If this distance from here to here, this distance is couple of meters or even 1 or 2 kilometers, we take the direction of G at all points as parallel. I hope this is clear to you. Now let us discuss the cases. In first case, the body is taken vertically upwards from A to a point B, which is at a height h above A, and you all know that the force acting here is G. The acceleration is G. So the force is going to be mg downwards. So work done by force from A to B will be minus mg h. But we take work from A to B by us. So that will be plus mgh, because that will be work done against the force. So work done by us, this is A to B by gravity. This is your against gravity. So we'll be taking against gravity. So let me erase this. So work done against gravity in this route is mg into h. In the second case, we take the body from A to C and from C to B this way. CB is an inclined plane, a smooth inclined plane. So now work done in this case, work done from A to B will be work done from A to C plus work done from C to B. Now work done from A to C, this will be 0 because we are not moving in the direction of force, that is mg. We are moving perpendicular to that. So there is work done is 0. So the work done will only be equal to work done from C to B. Now let's see what is the work done from C to B. Now you know that mg, the gravity acts downward, and this angle is also theta. So this is mg cos theta, this is mg sin theta. So work done from C to B will be the force is mg sin theta into BC, the displacement. Now H upon BC is equal to sin theta. So BC is equal to H upon sin theta. So here this will be mg sin theta into H upon sin theta, because H upon BC is equal to sin theta. So here sin theta gets cancelled. Again this is mg h. So work done from A to B in this case will also be equal to mg h. You can see in both the cases, here also it is mgh, here also it is mgh. Let's take another case that we take the body from A to B through this route A to C, and from here we have a staircase and we move the body on this is a smooth staircase and we bring it to B. Here we have n number of stairs and each of height h dash. That means work done from A to B will be equal to work done from A to C plus work done from C to B. Now this is already 0. Now work done from C to B. You take each stair, work done in climbing each step. That means you take from this place to this place. Now you can see for this portion work done is 0 because you are moving in the direction perpendicular. Only in this direction you have work done. So for a single step, the work done will be mg into the height of the step, which is given as h dash. H dash. So work done, hence for all stairs, that will be equal to, you have n steps, n into mg h dash. Now n into h dash is equal to h. So work done from A to B is again equal to mg into h, because n into h dash is equal to h. So you can see here also the work done is mgh. Suppose we are taking the body from A to C and from C to B in a zigzag kind of route. So first we take from A